Hello everyone, welcome back to my YouTube channel. So today we are going to solve day 20 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. So today we are going to solve problem number 3108, minimum cost walk in weighted graph. Okay, so this problem is actually marked hard by LeetCode, but let's make this problem a little bit easy. Okay, so let's read the problem statement first. Okay, so there is an undirected weighted graph with n vertices labeled from 0 to n minus 1. Okay, so see in this example n is equal to 5, so we have vertices from 0 to 4. Okay, 0 1 2 3 and then 4. Okay, so these are the vertices, right? You are given the integer n and an array edges, okay, where edges of I consist of total 3 values u, v and w, which indicates that there is an edge between vertices u and v with the weight of w. Okay, so see this example, edges. Okay, so this is u, v. Okay, this is my source, this is my destination. So if I move, there is an edge between source to destination with weight 7. Okay, so 0 to 1 there is an edge with weight 7. All right, 1 to 3 there is an edge with weight 7. 1 to 2 there is an edge with weight 1. Okay, so done. All right, so now a walk on a graph is a sequence of vertices and edges, right? So we have some vertices given to us, and if I want to move from vertices a to vertices v, definitely I'm going to use this edge, right? So we are moving from vertices to edges to vertices. Okay, a walk on a graph is a sequence of vertices and edges. Okay, the walk starts and ends with the vertex. Okay, so if I'm starting from here and if there is an edge between them, right, and then I will reach to this vertices. Okay, so walk is always going to start from a vertex and ending at a vertex. Okay, it's very common point. And each edge connects the vertex that comes before it and the vertex that comes after it. Okay, it's obviously right. And it's important, okay, now see this important line. It's important to note that a walk may visit the same edge or vertex more than once. Okay, so I can move from A to B, then back from B to A. Okay, so it's important to note that a walk may visit the same edge or vertex more than once. Okay, so this is the important line of this problem. Okay, this is the important line for this problem. All right, so just highlight this line. Okay, then after that, the cost of a walk starting at node u and ending at node v is defined as the bitwise end of the weights of the edges traversed during the walk. Okay, so let's say I am moving from this vertices to this vertices, then from this vertices to this vertices. Okay, and then so on. Okay, in the end this is my destination. Okay, so this is a and let's say this is z. Okay, and in this we have b, c, and here we have w1, w2, and here w3 to w, and let's say. Okay, so then okay, so the cost of the walk is going to be the bitwise end of this w1 and w2, then w2 and w3, then w3 and okay until wn. Okay, so this is going to be the cost. Okay, so this is also important line, bitwise end of the weights of the edges traversed during the walk. Okay, so mark it important. Okay, this line. Then in other words, if the sequence of edges weights encountered during the walk is wu to wk, then the cost is calculated as and of all these weights, where and denotes the bitwise and operator. Okay, done. Then after that, you are also given a 2D array query. Okay, so 2D array query given to us, where query of I has two values, one is s and one is t. Okay, so for each query you need to find the minimum cost of the walk starting at vertex s and ending at vertex t. Okay, and if there exists no such walk, then the answer is going to be -1. We have to return the array answer. Okay, output is going to be of array type, where answer of I denotes the minimum cost of walk for a query. Okay, and how we calculate the cost? Using the bitwise end of the weights of the edges traversed during the walk, right? And it is important to note that a walk may visit the same edge or vertex more than once. All right, so I hope that you guys are clear with the problem statement. All right, now let's understand this problem statement with an example here. Okay, so now here 0 to 1 there is an edge with 7. Okay, so first see this query. 0 to 3. Okay, 0 is my source. Okay, and this 3 is nothing but my target. Okay, source, and this is my target. Okay, 0 to 3 I want to move. Okay, so if I follow this path, 0 to 1 I move first, then I move 1 to 3, Okay, so then the total cost is going to be 7 and 7. Okay, so I'm doing the 7 and with 7. Okay, but here if you see, if I do the 7 and 7, so here how we are going to represent it in bit form. So here first 7 I'm going to write like this, 4 5 6 7, and another 7 is also I'm going to write like this. So my output is going to be 7 only, right? Okay, 7 only. So here if you see, 7 is not my output. Okay, so this is going to be the best path if we have to just calculate the summation of the weights. Okay, but here we are doing the bitwise AND. Okay, so here now if you follow this path, okay, if you move from 0 to 1 first, then 1 to 2, okay, then 2 to 1 back. Okay, we can traverse same vertices more than once, right? And then you move here. So if you follow this path, okay, this then this and this, okay, if you follow this path, so your total cost is going to be 7, and here 1. Okay, 1 to 2 you are moving, then 1, then again from 2 to 1 you are moving back, so again 1, and then again from 1 to 3 you are moving now, so you are doing 7. Okay, so now see this blue color part, do the AND operation of all this. So you know what is 7 and 7? It is nothing but 7 only. Okay, and 1 and 1 is also going to be 1. Okay, so this is AND property. Like if I do A and with A, I will always get A only. If I do B and B, I will always get B only. Okay, so same numbers having the same set bits, so our output is going to be same only. Okay, right? So this is my AND table, right? A and B here results, so 0 0, my output is 0, so 0 1 output 0, this is 1, this is 0, output 0, both are set, then my output is 1 only. Okay, so this is nothing but my AND table. So here 1 and 1 is going to be 1 only, 7 and 7 is going to be 7 only. Okay, now here just calculate the AND between 1 and 7. Okay, so 1 I'm going to write it like this, and 7 we already know, we write like this. Okay, now if you do the AND, so here 1, and here you are going to get just 1. Okay, 1 2 4 8, so output is just 1. Okay, so if you follow this path, you are going to get the best result, right? So to achieve the cost of 1 in the first query, okay, this is my first query, we need to move on the following edges: 0 to 1, okay, weight 7, then 1 to 2, then weight 1, then again 2 to 1, weight 1, then 1 to 3, okay, weight 7, done. Okay, so this is done, right? And now here if you see 3 and 4, 3 to 4, oh, there is no path now, there is no path, both are not connected. So in that case, simply return -1. Okay, done. Now from here, one more property that I can say here. So this is the first thing, and now second thing is that if I do the AND between any two numbers, okay, I will not get the output greater than these two. Okay, so what I'm saying, if I do the AND between A and B, let's say my output is C, so this C is always going to be smaller or equal to this A or B value. Okay, so we will not get C bigger than A or bigger than B. Okay, we are not going to get like that. Okay, so it's good if we are doing the AND of many numbers, we will always get the smallest value only. Okay, okay, so it's beneficial, right? We will get smallest or equal to, if all the values are same, then equal value, but if all the values are different, then we will get the smallest value. Okay, so you we can prove that, right? We can prove that. So let's say you have one vertex A, from A you are going to B, then from B let's say you are moving to C, then from C you are moving to W. Okay, so now here let's say this is your source and this is your target. Okay, so source to target, here you are moving taking 8. All right, now here C to B you can say that your distance is 2, okay, weight is 2, and here you can say the distance weight 1. Okay, so now one ways you can move from C to W directly, but in that case you are going to get output as 8. Okay, but there is best way na. So here if I can do one thing na, I can move from C to B, then I can move from B to A, then I can move from A to B, then B to C, and then C to W. Okay, I can cover all the connected vertices here with that particular vertex, right? So if I'm doing that, then definitely I will cover all the numbers, okay, all the weights, and I will do the AND. So here if you see this path, so first I am moving from C to B, then I am moving from B to A, then I am moving from A to B back, then I am moving to C, and then I am moving to W. Okay, so now in this case, let's see what is the output that I'm going to get. So C to B, 2 and 1 and again 1 and again 2, and now and with this 8. Okay, so you already know that 1 and 1 is 1, 2 and 2 is 2. Okay, 2 and 1 and 8. Okay, 8 here. All right, now here let's solve this now. So 8, 2 and 1. Okay, so you are going to write 2 like this. Okay, 1 0. Okay, and you are going to write 1 like this. Okay, in binary form, and your output is going to be 0 only. Nice, your output is 0. And now you are going to do 0 and 8. So 0 and 8, so 0 you are going to write like this, and 8 you are going to write like this. Okay, so you are going to get again 0. So your output for this is 0, but here you are getting 8, so 0 is my best answer, right? We have to return the minimum, and minimum is nothing but the AND of all the costs, right? All the weights. So this is done. So from here, one more thing that you can see now. So this is one complete component. Okay, this is one complete component. So in this component, I can do one thing. I can make any vertex as a parent, okay, as a father, right? So let's say this is a father. Okay, so here in this father, I will just store all the uh, weights and operation. Okay, so here let's say this is 8, let's say this is weight C1, cost 2, cost 3. So I will directly store the value of cost 1, cost 2 and cost 3. Okay, here, and I will make this as father. Okay, right? So I am just moving toward the DSU approach here. Okay, because I am dealing with the components. So this is one component, and let's say there is one more other component, and here in this vertex value you can say Q. Okay, now if I tell you to find this as my S and this as my T, then you will directly see now here that these two components are not connected. Okay, if these two components are not connected, then you are going to return -1. But if you want to find C to W or C to A or C to B, your result is always going to be the value which is stored at the parent or father, right? You can say father only, right? All right, parent child relationship you can prove, right? C1 and C2 and C3. All right, so now here this is clear, right? We are, if the two values, okay, if my source and target are in different components, then my output is going to be -1. But if my source and target are in the same component, then just make any vertex as a parent, and in that parent just store the values of the bitwise and of all the costs and just return that. Okay, that's it. All right, so now here how you are going to do that, so let's understand that. So here you can take this same example. Okay, so we have 0 1 and 3 and 2. Okay, 0, then we have 1, then we have 3, and then we have 2, and then we have 4 here. Okay, now here costs, if you write 7 7 1, okay, and 0 to 3 3 to 4. Okay, 0 to 3 we want to move. Okay, this is my query 1, and then 3 to 4 I want to move, and here course is nothing but here 7. Okay, undirected graph. Okay, and here 1, here 7, and that's it. Okay, so this is your example. So now here how many vertices we have? 4. Okay, so I will create one array. Okay, and I will name this as a parent array. Okay, so here this is 0, this is 1, this is 2, and this is 3, and this is 4. Okay, so right now what I will do, okay, initially I don't know that this 0 is connected with 1 or 1 is connected with 3 or 3 is 1 is connected with 2. I don't know. Okay, so I will make 0 as a parent of 0 only. Okay, this one's parent is 1 only, 2's parent is 2 only, 3's parent is 3 only, 4's parent is 4 only. Done. Okay, so I am making themselves as their own parent. Okay, then I will just iterate over the edges that are given to us. So here if you want to write the edges, okay, so let me just copy the edges here. So these are the edges we have, right? So let me just paste the edges here. Okay, so now you see that these are the edges, right? So 0 to 1, 0 to 1 there is an edge, okay, and 7 is the weight, okay. So initially I don't know this, initially I don't know this, okay, I don't know this, I don't know this, okay. So now it is saying 0's parent is 0 only, 1's parent is here you can write 1 only, 3's parent is 3 only, 4's parent is 4 only, and 2's parent is 2 only, okay. And here you can also mention the cost, okay. So right now cost, here you can say -1, okay, here -1, here you can say -1, all right, and here you can say -1 is the cost, here you can say -1 in the cost, okay, initially. Because if you do the -1, okay, and you do the AND operation with A, you will always get the output as A only, okay. So this is property, this is one property, okay. You can solve this, okay, and paste in the comment section, okay, how you are getting this, okay. You are always going to get A, okay, if you do the AND with -1, okay. So this is your homework, just try to find out, all right. So now this is done, okay. So now I'm saying 0 to 1, 7. So what I'm going to do, let's do one thing, let's make this 0 as a parent of 1, okay. I'm trying to connect these two, okay. 0 to 1 there is one link, so I'm going to connect these components, okay. So if I'm connecting with 0 to 1, which is having cost W, right? So I'm making 0 as parent, so initially 0's cost is -1, and now the latest cost is W for the connection, and this -1 is the cost which is coming from this one, okay. So I will do this, okay. So now both are connected with this. So here -1 and W is 7, and here -1, so I can write simply 7 here, okay, done. So now uh, I'm making the parent of 1 to 0 only, okay. I'm making this 0 as parent, okay, here, done, all right. So now this is one component. Then after that 1 to 3, 3 to 7, okay. So now here 3 is going to come, right? So 0 I'm taking it as a parent only, right? So here 3 is going to come, okay. So if 3 is coming here, so initially cost of 3 is -1, so 7, okay. This is the 7 is the cost of this 0, okay. And here 3 is cost is -1, and now the link is 7 only, so 7 and -1 and 7, it is going to give me 7 only, okay. Again 7 only. Now 3 is connected, okay. 3 is connected here, okay. Now after that 1 to 2, 2 to 1, okay. So 2 is going to come here. So if 2 is coming, so 7 is the cost initially, okay. Then 2 -1 is the cost after connecting 2, okay. So 7 and -1, and the cost in between, okay, for this particular, so is 1, okay. So 7 and -1 and 1, you will get output as 1 only, okay. So this is done, okay. Now all are connected here, all right. And here 2's parent is also going to become 0, and 3's parent is also going to become 0, all right. So now after that you have to iterate over the queries. So 0 to 3, 0 to 3, so here you will just find out that 0's parent is 3 and 3's parent is also 3, also 0, okay, 0. So that simply means that they have same parent. So if they have same parent, that simply means that they are in one same component. So if they are in same component, then just check the parent value, okay. So in at top of parent we have 1 written, okay. So during this formula we have calculated 1, okay. So 1 I'm going to write output as 1, okay. Then 3 to 4, so 3's parent is 0, 4's parent is 4, so parents are different. That simply means that they are in different components, so that simply means there is no link between them. So if there is no link, so we have to return -1, okay. That's it, all right. So now let's write the code, okay. But I hope that you guys are clear with the explanation. We have covered in just 18 minutes, okay, everything. Yeah, that's nice, right? We didn't waste much time, all right. So now let's write the code, okay. Code is going to be very simple, all right. So now I think I made this problem a little bit easy for you guys, right? Okay. So now first just write a few things, like create one parent array, okay, parent array, and new int, and here you have to give the n, okay. And then you can create one cost array, right? So let's say this is my cost array, and here new int n, all right. And then you can create one result array as well, okay. So int result is equal to new int, and here you can pass the query dot length, okay. So result size is going to be of query dot length, okay. done. And then initially you can fill all the costs as -1. Okay, so I told you that if I do -1 and with a, I will always get a. Okay, so arrays dot fill, that is why I'm taking -1. Okay, if I take 0, I will always get 0 only, so I can't take 0. Okay, I have to take -1 only. All right. Okay, this is done. All right, now after that you have to iterate over all the vertices that you have, and you have to make them their own parent. Okay, so int I is equal to 0, I is less than n, and here you have to write I plus plus. Okay, and inside this you have to write parent of I. Okay, and you have to set it to I only, right? And then you can iterate over all the edges one by one. Okay, and then we will just update the parents, okay, and the costs. Okay, so that stuff we will do now. So for int, you can use for each loop. Okay, so we are iterating over array, right? So here I have to write like this, int h. All right, and here edges. All right, and inside this we have to calculate u, right? And u, I can say edge of 0. Okay, then you have to calculate v, you can say v as edge of 1, and then you have to calculate w. Okay, you can say it as edge of 2, right? So we have total 3 values in a particular edge, right? U, v, and w. Okay, then we have to find out the parent of u and v. Okay, so int parent of u. Okay, and here you can call this find method. Okay, in the find method, what you are going to do, you are going to pass the value of this u, okay, and the parent array. Okay, all right. So now again you are going to find the parent of v. Okay, so here again you are going to call the find, and now you are going to write v, and here you are going to calculate the find the parent of this. Okay, so now here if the parents are not matching, okay, if parent of u and parent of u is not equal to parent of v. Okay, so if the parents are not matching, then in that case we have to update the cost. Okay, so cost of parent u. Okay, parent underscore u. Okay, I will just do the and of this one, and with cost of parent of v. Okay, so this is done. Okay, cost of parent underscore b. Okay, this is done. So here if you see, we are doing the and. Okay, so when I'm connecting with this 0 with 1, okay, so this cost and this cost, I'm doing the and. I have to do this as well. Okay, so right now I'm just doing the and of these two 0 and 1s. Okay, which is -1 right now initially. But okay, this is one thing that I have to do. Then also I have to if I'm connecting, then I have to find out the common parent, right, for them. So here in this I will just pass parent of u value, parent of v value, and then here I will just write parent array. Okay, and I will update. Okay, this union method is going to update, and here I'm doing this now, but I have to add this w as well, right? And I have to do the and as well. So here after this, if I have to write what is the whatever the cost of my parent u. Okay, so I'm making parent of u as a parent. Okay, let's say, and I'm just going to do the and with w. Okay, this is done. So that's it. Okay, so this is here our code ends for these edges. Okay, now we have to iterate over all the queries. All right, so here for int I is equal to 0, I is less than query dot length. Okay, and here I plus plus. All right, and then after that int s. Okay, so s value is at query of I and 0. All right, and then int t, and t value is at query of I, and here you have to write 1. Okay, and then after that you have to check the parent of both. So int p1. So how we are going to find the parent? So again call this find. Okay, and find will help us in finding the parent of this. So s I'm passing, and here in the parent array I have to pass. Okay, and I'm calculate the p2 parent. Okay,
is equal to, again find, and here t, and here parent. Okay, so this is done. And then here I will check if s is equal to t. Okay, so here I am saying that if my source and target both are same, then simply return 0 now, then we are not moving anywhere, right? So here result of I am going to update it to 0. Okay, for this particular query. Okay, query I. All right, and else if my s is not, oh, not s, here you can check a parent. Okay, if both the parents are not matching, okay, that's implement that there are two different components. Okay, so in that case we have to update my result of I index as -1. Okay, and in the else part just update my result of I as the you can just pick the cost of that particular parent. Okay, so parent is same now, so you can write p1 p2 anything area. Okay, done. So this is what you have to do here. Okay, now after executing all this query, then you have to simply return result. Okay, now everything else is done, but we have to write this find and this union. This is very simple. Okay, so now here after line 37, okay, only few lines, 4-5 lines, that's it. Your question is complete now. Okay, solution is completed. Private int find. So in find you are passing two things. Okay, one is that particular vertex and one is the parent array you are passing. Okay, in the parent. So now here first thing, that if the parent at that particular index value, okay, if it is equal to x, okay, that simply means that initial setup, whatever the initial setup was there. Okay, so then we have to return x. So here if you see, I am finding u and parent. Okay, so I am finding the parent for this, I am finding the parent for this. Okay, so if both are here, if the parent of x is equal to x, okay, initial value, right, parent of 0 is 0, parent of 1 1, parent of 2 2, so we have to return same only na. So here I will just return those parents. Okay, so after that we are checking if both are not matching. Okay, so but here let's complete this first. Okay, so if parent of x is x, so I'm just returning x. Otherwise I have to, what do I have to do, I have to update, check here, return parent of x. Okay, parent of x I am going to update. Okay, parent of x. Okay, if this value is not equal to x, okay, then what I have to do, I have to return parent of x. I am going to update it. Okay, so here I will then find, okay, I will find it, okay, later on. So find of parent of x. Okay, so here I am going to find the parent of x. I am going to write that, and then again I'm passing the parent. All right, so it's like this. Okay, so let's say 1 is a parent. Okay, and here 3's parent is 3. Okay, 1's parent is 1. All right, so now both are uh, different. Okay, both are different. Okay, so here we are just returning that, but here if you see how I'm searching, I'm searching for the okay, so if here both are different. Okay, but let's say if at index 3 I have 1 here, let's say I have operated it to 1. Okay, 1 only, so 1's parent is 1, 3's parent is 1. Okay, so now at parent of 3, okay, parent, and here I am finding it for x3. Okay, so parent of 3, parent of 3. Okay, so here I am checking if it is equal to x. Okay, if it is equal to 3. So right now here see parent at 3 value is not 3 but it is equal to 1. Okay, so this is not correct, right? Then what we have to do, we have to update my parent of x as, so parent of 3 I'm going to update it as parent of 3. I'm going to update it as, okay, I'm going to update it as, again I'm going to call find. Okay, and in find now I am parent of 3. Okay, here I am x, finding value of x as 1. Okay, and here parent. Okay, parent array I'm passing. Okay, so now this time it will match, so this time it will match, right? Parent of 3. Okay, and then here I'm calling find 1p, so at 1 it is matching, so that simply means that 3's parent is also 1, there is connection. Okay, so at 3 we are storing 1. Okay, so from here we just reach to here. Okay, that's it. All right, this is done. Okay, now after that union is very simple. Okay, just one line of code, private void union. Okay, and let's say two parents int x int y. Okay, and here my parent array. Okay, int parent. All right, and now after that what you have to do, you have to make parent of y as x. That's it. Parent of y is equal to x. All right, done. Okay, so this find is always going to find the parent. Okay, so here let's like this, right? 1's parent is 1 and 3's parent is 1, but you see at 3 parent is not 3, so again you have to call this parent of 3 is going to find. Now you have to find this 1. Okay, and going to reach here. Okay, here only. So this, from here you are going to return parent as 1. Okay, that's it. So this is done. Let's run it. Okay, only 47 lines of code. Let's run it and see if there are code issues. So all the test cases has been accepted. Now let's submit it. So see, our solution is accepted, right? So I hope that you guys are able to understand today's problem. And if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.